All right, students, so here we are on number 9. This is called composition of functions. That little open circle is not a multiplication symbol. So let's go ahead and grab number 9. I'll show you what to do. And guess what? You've been doing it all along. So this is going to be review, since we've literally been doing this the whole time. All right, where am I going to post this? I think I'll post it here. So, as I said, you've done this already. So the question's asking you to compose the function g with the function h. And all that really means is what you've already been doing, which is to say g composition h of x is equal to g of h of x. See, you've already been doing that, right? So this is equal to 4 open parentheses x cubed minus 1 close parentheses plus 5. So the composition of the functions g and h of x is equal to 4 open parentheses x cubed minus 1 plus 5. So let's keep it rolling along. The composition of functions g and h of x is equal to, and now we're going to distribute 4. So we have 4x cubed minus 4 plus 5. And there's just one more step. The composition of functions g and h of x is equal to 4x cubed plus 1. And you are done with number 9. So function composition is something that you've been doing every single time you've validated your inverse function. It's the same thing. It's just a different notation. So let's go back. So 4x cubed plus 1 So what we're going to write down as our answer is the composition of functions g and h of x is equal to 4x cubed plus 1. Moving on to number 10, it's another composition of functions, and this is the composition of f and g. So at this point, if you've been validating all of your inverse function problems, you've done this 8 times on this paper already. So we'll put number 10 right here. Now let's move that and resize it so it's about the same size as the other one. Okay. So, composition of functions f and g of x is equal, or I should say equivalent to, f of g of x, okay, which is what you know how to do already, which is equal to 3 open parentheses 3x plus 2 close parentheses. So the composition of function f and g of x equals 3 open parentheses 3x plus 2, and then we do the distributive property. And we find that the composition of functions f and g of x is equal to 9x plus 6. So the composition of functions f and g of x equals 9x plus 6. And that is the answer. Not hard at all, right? So 9x plus 6. So the composition of functions f and g of x is equal to 9x plus 6. Now, in the next two problems, we are asked to add the functions together. Well, in the next problem, we're asked to add the functions together and then evaluate the sum of those two functions at -1. And then in number 12, we were going to subtract function f from function g, and then we take the difference of those two functions and we evaluate that difference at -9. So let's clip out number 11. And find a place to put it. Put it right here. So I have a way of adding functions together that might be a little bit different than the way that you have been taught thus far. I use a method where we stack the functions. So certainly, if the way that you've been taught to do g of x plus f of x, where g of x equals -3x squared plus 2, and f of x equals x minus 3. If the way that you've been taught to do this thus far is to simply write down negative 3x squared plus 2 plus x minus 3, and then combine like terms. You would get negative 3x squared plus x minus 1. And the only two terms that you would combine are positive 2 and negative 3. Now, what they want us to do is evaluate that, right? So this is g plus f of x. But now they want us to do g plus f of negative 1. So what we would do is simply substitute in everywhere we see an x, a negative 1. Okay, the order of operations becomes extremely important here. So g plus f of negative 1 would equal negative 3, and then you do this first. You square negative 1. Now, squaring a negative number makes it positive, and 1 times 1 is 1. So this is negative 3 times 1. And then plus negative 1 just means minus 1, and then minus 1. Now, these two things together is like saying negative 1 plus negative 1, which would equal negative 2. So g plus f of negative 1 would equal negative 3 times 1 is just negative 3 minus 2. So g plus f of negative 1 would equal negative 5. So if that's how you've been taught to do these problems, it works when the problems, it works pretty easily when the problems are really simple. Okay, when the given functions are straightforward, especially when you're only being asked to evaluate an integer value, okay, like a whole number or a negative number where it's just a number, it's not a fraction, or especially it's not an algebraic expression. This can get way more complicated. So I suppose in this particular case, it's not really important whether you use the stacking method or the method where you just write it all out. But I want to show the stacking method because as these problems get more complicated, the stacking method is one way of making sure you make no mistakes. So we'll call this method 1. Okay. And then this is, my method is called the stacking method. Let's see if we get the same thing, and let's see what you think of it. Okay. So the stacking method, what it has you do is it has you create columns based on the exponents. Okay, So here the exponent is 1. That's important. So each exponent gets its own column. So in the stacking method, we're going to add g plus f, right? In the stacking method, we would write negative 3x squared. And then notice that we don't have anything in g of x where it's just x by itself. We just jump right to the whole number. So what we would do is we would put in plus 0x. Okay, because that's 0x to the first. And then we'll put plus 2. Now beneath that, we have x to the first minus 3. So remember, we put the exponents and group them together in columns. Okay, so here we would put 1x to the first, and then we would put plus negative 3. And now, like I said, this particular problem, it doesn't really matter. And unfortunately, you're not given any problems in this problem set where it does matter. But I'll just show you the method. So we create these columns, and you just add the columns. So like here we have 0x squared. So we just add column by column. Negative 3x squared plus 0x squared is negative 3x squared. 0x to the first plus 1x to the first is just plus x. 2 plus negative 3 gives us negative 1. And so you see we've arrived at the same sum as we did here. And then you would just evaluate that at negative 1. So you would say g plus f of negative 1 equals, well, I don't want to get rid of the columns because I want you to see them in your notes. I'll just write this lower. G plus f of negative 1 equals negative 3, open parentheses, negative 1 squared plus, open parentheses, negative 1, close parentheses, minus 1. So again, g plus f of negative 1 would equal negative 3, and then negative 1 squared is 1. And then we just have minus 1 minus 1. So g plus f of negative 1 equals negative 3 minus 2. So g plus f of negative 1 equals negative 5. And again, you're going to get the same answer both ways. What I'm trying to warn you about is down the road, when you're evaluating something much harder than just a number, and when your original given functions are way more complicated than this, the stacking method can save you, especially when they're all mixed up, like they're not in order. You have to reorder them. You could even be given like 5 functions and asked to add all of them together, and it just, if you were to try to write it out in one big line, it would become a complete nightmare of trying to find the like terms. And so the stacking method's benefit is that it does the like terms part automatically. Okay, that's the benefit of the stacking method. So personally, I recommend the stacking method. Here's one thing that I absolutely do not recommend that you do. Notice that in both of these methods, first thing I did was I added the 2 functions together as functions of x. And then only when I had the sum of those 2 functions did I actually evaluate at the number that they wanted us to evaluate. What I see in a lot of the homework problems and the tests that I'm grading, even in pre-AP, is I'm seeing students attempt to jump and plug the -1 in the very first step. And that is, there are so many chances for errors when you try to do multiple steps at once. It's also not mathematically accurate to do it that way. The problem is asking you to do a certain thing in a certain order. The sequence is add G and F and then evaluate that sum at -1. It doesn't say plug in -1 everywhere you see an X and then add it all up. That's a recipe for disaster. Okay? It's a shortcut, but it's going to get you in trouble. So anyway, in this case, G plus F of -1 equals -5. I'm just warning you. So we write G functions G and F, the sum of functions G and F evaluated at -1. See, when I say it that way, it actually tells you what to do. The sum of G and F, okay, evaluated at -1. So there's a step in there where it wants to see the sum of G and F. If you're just plugging this number directly into the functions and then adding it up, you're not actually finding the sum of the functions. You're just plugging numbers in, okay? So anyway, let's move on. I wish they'd given you in this test review a harder thing to evaluate, so it would just very clearly demonstrate what is wrong with the method of just trying to plug it in real quick and rush through the problem. So let's do number 12. This is a subtraction, and subtraction, in my opinion, makes the stacking method even more crucial, because otherwise you're going to have to distribute a negative. So let's go here, and this is number 12, and we'll put number 12 right here. So here we're asked to subtract f from g first, okay? So basically, you need to ignore that -9 and just do this for x first, okay? And then do it for -9. All right? That's how I'm going to teach it, and that's how I want you to do it, so that I can see that intermediate difference as a function of x. Okay, so I'm going to use, again, both methods, since some of you have only been exposed to the method that I said I don't like. So here's that method. I guess I'm going to call it the line method. Maybe this will demonstrate to you something. So what you're going to do is you're going to take g of t and subtract f of t. Okay. So what does that look like? Well, g of t is 4t plus 4. And then you're going to subtract t plus 1. Now, if you write it like this, you're going to get it wrong. Okay? Because you must distribute that negative symbol. So even if you're going to use the line method, a much better way to write it would be g minus f of t. Okay, I wrote x over here, I meant t, equals 4t plus 4 plus, and then you go off to the side, you're going to write -1, okay, in parentheses. And then you're going to do an open parentheses and write t plus 1. And then you're going to close those parentheses off. And that is going to tell you what you need to do, right? You got to distribute that -1. Otherwise, this whole thing falls apart. So what would that equal? 4t plus, except we're going to have t's and pluses that look the same, 4t plus 4. And then let's see what happens. We get -1 times t is minus, and then I recommend writing 1t. All right, so you know what the coefficient is. That's another landmine. -1 times 1 is just -1, which I would prefer that you write plus -1, like that. There's a reason for it. So now you're going to combine like terms. So here are the linear terms that are like, and here are the constant terms that are like. Okay. So that was g minus f of t. Notice I still haven't messed with this -9 at all. So let's now combine the like terms. We have g minus f of t equals, now let's do the pinks, 4t minus 1t is 3t. And then 4 plus -1 is 4 minus 1, and that's -3. Okay? Now, I see something that we can do, and you can only see this if you first find the difference of the two functions of t and not of the number. Okay? I see something that we can factor out. And again, right now, it's not absolutely crucial that you do this, but the greatest common factor of those two terms is 3. And so you can actually pull that 3 out like this. You're basically dividing it out. Let me show you what that looks like. So now function g minus function f evaluated at t is now equal to 3 open parentheses t minus 1. Okay? This isn't important right now, but it will be important later that you know how to factor out the greatest common factor. So this would be a step that I would like to see, regardless of whether you use the line method or the stacking method. So now we're going to evaluate this at -9. So we have g minus f, or the difference of functions g and f, evaluated at -9 equals 3 open parentheses, and then we're going to do open parentheses -9 where we see the t, close parentheses, minus 1, close parentheses. Okay? So the question is, we do what's inside the parentheses first. What is -9 minus 1? -9 plus -1 is equal to -9 minus 1, which is equal to -10. So I like to think of the minus, I like to think that there is no such thing as subtraction. There's only the addition of negative numbers. I read that in an advanced math book one time. So we have the difference of functions g and f evaluated at -9 equal to 3 times -10. So the difference of functions g and f evaluated at -9 is equal to -30. Okay. That is the line method of doing this. So what would the stacking method look like? Again, don't judge the method by this problem, because this is too simple for the method that I'm proposing to show its true benefits to you. But here's the stacking method. Now I'm telling you, there's going to come a time in this class when the only way to do it is to stack it, or the only way to do it with any reasonable chance of getting it right is to stack it. So we don't have any quadratic terms that would mean t's raised to the power of 2. We just have the linear terms where the exponent is 1. And remember, in front of that t there's a 1. So what we would write is we're subtracting f from g, so we put g on top. 4t plus 4, and then underneath it we would write 1t plus 1, and we put that in parentheses because we're subtracting, and we put a big minus sign out here. And we take our ruler, draw a line, then we make our columns. Okay. Now, in this case, there's only one column, right? And it doesn't even need to be that long. It just needs to be like this. So here's how you do this. I'm going to use a different pen. You say with your finger, 4t minus 1t. 4t minus 1t is 3t. All right, so let me get rid of all those dots. So the dots represent you with your finger on the paper, right? So 4t minus 1t equals 3t. And now you come over here. And again, this dot is your finger. 4 minus 1. Right? So your finger is moving to the minus symbol, and that's essentially performing the distributive property. You're just saying it in your head. 4 minus 1 is 3. Okay? So, positive 3. Let me get rid of the dots. So we put plus 3. So let's see what we have here. The difference of functions g and f with respect to t, okay, or evaluated at t, is equal to 3t plus 3. Okay, I just noticed a mistake in my own work. Over here, when I was combining like terms, 4 plus negative 1 isn't negative 3, it's positive 3. So this would be t plus 1. So when we evaluated it, it was going to be negative 9 plus 1. Not negative 9 minus 1. So this is negative 9 plus 1 equals negative 8. Well, I don't want to delete. I want to show the wrong work and then scratch it out, okay? So this should have been minus 8 which means this should have been negative 24. All right, let's see if we get the same answer here. That kind of just proved my own point, I think, there. The reading left to right method and combining like terms is prone to error, where the stacking method is much less prone to error. So there's a perfect demonstration. All right. So now we can go ahead and evaluate this at negative 9. But before we do that, let's do the thing that I noticed before, which is that we have a greatest common factor that we can factor out. In this problem, that greatest common factor is 3. So that can come out here. I'm telling you, later on, factoring out the greatest common factor will make your life infinitely simpler. Even though in this particular problem, it's kind of irrelevant. G minus f of t equals 3, open parentheses, t plus 1. Okay, you see how the thing inside is now simpler? You've also factored this, which becomes important later on in Algebra 2. Factoring by grouping requires you to factor out the greatest common factor twice. So honing that skill now will help you later on. So now let's do the difference of function g and function f evaluated at negative 9, which would be equal to 3, open parentheses, and then open parentheses, negative 9, close parentheses, plus 1. So the difference of functions g and f evaluated at negative 9 equals 3, open parentheses, negative 9 plus 1 is negative 8. So the difference of g and f, functions g and f evaluated at negative 9, is equal to negative 24. In my opinion, it is utterly crucial that you get to this point here. And there's a reason for that. And I'll tell you the reason right now. I'm going to make the point. Why is it important that you arrive at the function, the difference with t, with respect to t, and not just jump right in and plug in the number? Okay, here's why. Let me open up a browser window and go to Desmos. I'm going to prove a point to you. No pun intended. I'm literally going to prove a point to you. So, negative 9 is the input value. That's always thought of as kind of like the x value or the independent value or the domain value. Okay, input x, independent domain. Okay, these are all words that describe negative 9. in this case they were using the letter T, okay? Whatever, all right? The thing inside the parentheses that you're evaluating the function at is the input, the independent variable or number, the x or whatever letter they're using, or the domain value, okay? This is the value along the horizontal axis. Okay? Now, in a similar fashion, let's use blue. Negative 24 is the output value. That's what we typically call y, or f of x. Okay, or in this case, we're calling it the difference of g and f. Okay, this is the dependent number. In other words, this number depends on what you plug in. It changes depending on what you plug in. And this is what's going to be plotted as the range value. And this is going to be on the vertical axis. Okay? So all of these things describe negative 24. The thing I want you to pay attention to is this is x and this is y. So if you put them together with a comma in between them, you have a coordinate pair. So if I rewrite g minus f of t as y, then I have, back to my original equation, this is why it's so important, I have y equals, remember this, all of this gets replaced with just y. Y equals 3, open parentheses, and then to turn this into an equation that we can graph in Desmos, we're going to replace that t with an x. So y equals 3, open parentheses, x plus 1, close parentheses. Y equals 3, open parentheses, x plus 1, close parentheses. Well, now, if you wanted to write this in slope-intercept form, it becomes obvious. You would just redistribute the 3, and you'd have in slope-intercept form y equals mx plus b, where m is the slope and b is the y-intercept. You would have y equals 3x plus 3, which tells you that the slope is 3. So that's a rise of 3 and a run to the right of 1. And this over here is the y-intercept, right? That's the y-intercept. And this tells you that the line crosses the y-axis at 0, 3. Okay? So here's your slope, and here's your y-intercept. And if you had to, you could go and create a graph, which I'll do right now, and sketch this function with no trouble whatsoever. Okay, let me show you how easy it is to sketch this function now that you have this information. So I'm going to delineate here 1, 2, 3, 4, 5, 6, and I'm going to call this y and this x. Remember? And then using the same spacing 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. It's not perfect. Doesn't matter. 2, 3, 4, 5, 6. Okay, so what I'm going to do first is plot my y-intercept. And that would be located at 1. So this is the origin point, 0, 0. This is 0, 1, 0, 2, 0, 3. There's my y-intercept right there. Okay. So I want to make this note. Right there is my y-intercept. And that's located at 0, 3. Now from that point, I can plot the entire line. All I have to do is use the rise and the run. So I'm going to rise up 3, and then I'm going to run to the right 1 space, and I'll place my next dot. So look, you rise up 1, 2, 3, and then you run 1 to the right. So over 1. Right there is another point on the line, and you only need 2 points to plot a line. But we could do it again in reverse. So instead of doing a rise of 3 and a run to the right of 1, we could do a fall of 3 and a run to the left of 1. Okay, so now we have 3 points plotted. And if you have a straight edge, it's very easy to draw or sketch quickly the graph of the line. Let me find a color we haven't used yet. Blue. So there's your line. Right there. That's what it would look like. And the equation of that line is y equals x plus 3. But this is also, y equals 3x plus 3. But we can now substitute back in g minus f of t in function notation. We could say g minus f of t equals 3t plus 3. And this line is also described, okay, by that function. So here's the point I'm getting at here, and this is why I want to use Desmos. Functions can be written as lines, as the equation of a line. It is really important that you understand these things, okay, about the input and the output, so you understand what you're doing. When you input -9 and you evaluate the difference of g and f, you get -24. So what that means is that somewhere on that graph that we just drew, which we're not going to draw out to be big enough to see these points, but here is what I'm trying to tell you. Somewhere on this line, okay, somewhere on that line, this is the one I'm going to plot in Desmos. Somewhere on that line is the point -9, comma, -24. Guaranteed. And if it's not on the line, then we did something wrong. Okay? So let's go check. We'll write y equals 3x plus 3. And then we'll put in the coordinates -9, comma, -24. Okay? And I'll label that the point. Okay? Let's zoom out and see. Look at that. There it is. So it's on the line, isn't it? And that's the point I was trying to make to you. Now look at the line. Doesn't the line look just like the thing we sketched? We determined it looked pretty darn close, like it crossed the x-axis at -1, comma 0. The x-intercept being -1, comma 0. Let's see if we were right. Wow. So you didn't need a calculator or a computer. You could just draw it. Okay? And now we know a lot more about this topic than we used to. Okay? And I want to make this point. This is the input of -9 and the output of -24. Okay? So I'm going to save this graph. What number is this? Number 12. I'm going to save this graph as number 12 from test review 1-1 Alg 2 academic Morelli, and then today's date 09/04/2021. Let me save that and let me share it and paste it into the OneNote so that you have access to this. Is it frozen? Okay, there we go. What's going on? It's like it's frozen. Hang on a second. Okay. Yeah, it was kind of frozen up there for a second. So now, if you were to load this up in your class notebook, you would actually have a working version of Desmos right here inside your class notebook that shows that point plotted on the line so that you remember the relationship that I'm talking about here. Okay, so let's get back to just answering the question. So the difference of G and F evaluated at -9 is -24. Just hoping I can get this written down, and then I will give the computer a break. I can tell it's overworked. Let me close this browser. That should help. Okay, I think I'll be able to get this written down, and then we'll have to take a break and let the computer cool down. So the answer to the question is the difference of functions g and f evaluated at -9 is -24. Okay, so that's what you would write, but you saw all the work that we did on this side. So we'll take a break and let the computer cool down, because I can feel the heat on the touchscreen. When I use the pen on the touchscreen a lot, and especially when I've got multiple applications running and I'm recording, it's just maxing out the CPU and it's throttling down and it freezes the computer. So let's give the computer a break, and when we come back, it'll be cooled off and we can continue.